What you are looking at is a tragedy. Some time ago, we acquired this rusty Oldsmobile big block motor for the price of scrap. What we didn't know at the time was that it had 0 hours on it. It had never been fired. But through a failure of storage, a cracked plastic shipping cap allowed rainwater to seep into the intake, pooling in the cylinders. However, we would discover that there was a silver lining. Because this engine never endured the heat cycles of a vehicle or the heavy-handed work of a local machine shop, it remains a pristine, 0-hour time capsule. Every factory inspector's mark, every stamp, and every casting number is exactly as it left the Lansing engine plant after it was assembled all those years ago. Today, we are going to do a forensic teardown of this mystery motor, an archaeological deep dive, if you will. We aren't just taking it apart, we are going to decode its identity using the original factory assembly manuals to prove exactly what this machine is. With the help of Dr. Oldsmobile himself, as well as his lab assistant, we'll start from the outside, establishing the engine's DNA methodically. So strap in, we are about to rocket back in time to an era where American muscle was gasping for air, but not completely dead yet, as we will see. First, before we tear it down, let's look at the clues on the skin of this beast. The first thing that jumps out is the remnants of black paint on the valve covers. In the Oldsmobile world, this was our first major hint. Passenger car engines were rocket gold or Olds blue, depending on the year, but black valve covers were the standard issue, uniform, for Oldsmobile's heavy-duty industrial and marine applications. We were definitely looking at something built for work, not the street. Next, we checked the carburetor. Stamped right onto the side, we found 7042953-RL. This is our first real decoder ring. The 704 tells us it's a Rochester Quadrajet. The 2 designates a 1972 model year, and that 9 is the factory fingerprint for special/marine industrial use. Right away, the carb dated this engine to 1972. With the carburetor confirming a 1972 build, we looked for performance clues in the top end. At first glance, we saw a massive G cast into the cylinder heads, which was the standard 1971 Olds performance casting. But when we looked closer, there was a crucial detail right next to it, a small lowercase a. This makes it a GA head, and that changes everything. The GA head was introduced specifically for the 1972 model year, featuring induction-hardened exhaust valve seats to handle the incoming unleaded fuels. Finding the GA casting instead of a standard G is a huge win. It means these cylinder heads perfectly match the 1972 date codes on our carburetor and our starter. Furthermore, when we cross-reference the 1972 assembly manuals, the GA heads used on these marine packages were the heavy-duty variants, retaining the massive 2.072-inch intake valves from the previous high-performance years. The entire top end was breathing heavy and perfectly matched to 1972. Then we found the block casting number, 39602-1F. The 396021 is the definitive high-strength block Oldsmobile used for their 455s from 1972 onward, and the F marks it as a central foundry casting. This wasn't some leftover parts bin build. This was a brand new top-tier block pulled off the line specifically for this 1972 crate package. Finally, we checked the left-hand block pad. If this 455 had been dropped into a 1972 Cutlass or 442, this pad would be stamped with a 9-character VIN derivative. This tied the engine to the exact car chassis it was bolted into on the assembly line. But look at our pad. It doesn't have a GM passenger car VIN. Instead, it is stamped with a bizarre, non-standard code, L2E over 1544H. This proves 2 things. First, because it lacks a car VIN, We know for a fact this was a service AFA crate engine. It bypassed the normal car chassis line completely. Second, that bizarre stamp is a specialized tracking serial number. When marine outfitters, like Hardin Marine, OMC, or Crusader, bought these heavy-duty crate engines from Oldsmobile, they arrived with blank pads. The outfitter would then stamp their own proprietary sequential numbers right into that empty space for warranty tracking. That 1544H code is the outfitter's fingerprint, cementing the fact that this engine was processed, cataloged, and prepped for a high-performance life on the water. But here is the craziest part of this entire forensic investigation. Despite being fully dressed, stamped, and ready to go, this engine never made it into a boat. It was never fired. On this engine, the identification code decal, which should be on the oil fill tube, is long gone, and the sequential serial number stamp is pretty much meaningless to us, so we will have to look elsewhere to determine exactly which engine we have here. To break the tie on exactly which marine package this is, we looked at the ignition. Our distributor is stamped 1111982 with a production date code of 1L7. In Delco Remy language, the 1 means 1971, the L is the code for November, and the 7 is the day. This distributor was built on November 7th, 1971, but it's the part number that is the real smoking gun. The factory charts from 1972 explicitly reserve part number 1111982 for the marine performance packages. A standard marine engine would have received a different unit, and right next to it, our heavy-duty starter, part number 11-08389, stamped 1L16, built just 9 days later on November 16, 1971. This isn't just a random assortment of parts bolted together decades later. We have confirmed this is a factory-batched 1972 marine high-compression performance crate engine, and the date codes prove all these accessories were brought together at the Lansing plant at the exact same time. So the factory manual told us we had a 325 net horsepower marine engine. But the math told us that with a 10.25 to 1 compression ratio and a W30 camshaft, this thing was actually pushing closer to 390 gross horsepower. And then we found the missing link. This is an original set of vintage marine valve covers. Cast right into the aluminum is Hardin Marine, one of the biggest, most legendary jet boat builders of the 1970s. Suddenly, that mysterious 1544H stamped into our block pad made perfect sense. The H stood for Hardin, but look at the sticker they applied to the cover, 390 horsepower. Because marine outfitters weren't bound by the strict automotive emissions and rating laws that choked Detroit in 1972, Hardin Marine didn't have to use GM's neutered net horsepower numbers. They knew exactly what Oldsmobile had shipped them, a completely unrestricted, high-compression W30 spec monster. They rated it at its true 390 gross horsepower, slapped their sticker on it, and dropped it into their jet boats. Our engine is a 0-hour Hardin Marine 390 horsepower time capsule. Now let's tear off the oil pan and prove that the internal hardware backs up the badge. Thanks, Ernie, I guess. With the GA heads finally unbolted and on the bench, we get our first look at the internal hardware. And because this engine never ran, the original assembly line markings are completely pristine. Notice the paint dabs on the valve springs and the valve heads. In the Lansing engine plant, these weren't random splashes of color, they were quick reference codes. The line workers used these specific color combinations, like the green and white dabs we see here, to ensure that the heavy-duty, high-tension marine springs and the correct valve materials were being dropped into these performance heads, preventing them from getting mixed up with standard passenger car components. When we flip the head over, the sheer size of the GA casting's breathing capability becomes obvious. These heads are stuffed with massive 2.072-inch intake valves and 1.625-inch exhaust valves. But it's the void around those valves that tells the real story. The combustion chambers in these heads measure right around 80 cubic centimeters. To understand why that matters, we have to look at what is sitting inside the engine block. These are the original factory pistons. In 1972, General Motors mandated that all passenger cars run on low-lead fuel. To do that, they neutered the compression in the streetcars by using deep dish pistons, scooping out about 40 cubic centimeters of volume from the top of the piston, dropping the compression ratio to a sluggish 8.5 to 1. But look at ours. These pistons feature a very specific V-notch and a specialized ultra-shallow dish measuring roughly 14 cubic centimeters. This is where the math of our marine spec sheet comes to life. When you take the 80 cubic centimeters volume of the GA combustion chamber, combine it with the incredibly shallow 14 cubic centimeters dish of this V-notch piston, and seal it with a thin factory steel shim head gasket, you squeeze the air and fuel into a tiny, highly pressurized space. This specific combination yields exactly 10.25 to 1 compression. While the 1972 streetcars were choking on smog regulations, this marine block was built using the exact same high-compression architecture as the legendary 1970 W30 muscle cars. And the only way an engine with 10.25 to 1 compression can breathe properly is with a radical camshaft to match. Let's pull the front cover and see if the beating heart of this engine matches the blueprints. But first, we needed to get to work on those rusty cylinders so we could continue the disassembly of the short block. The good Dr. Oldsmobile made prodigious use of a product called evaporust to chemically unlock the decades of corrosion that was binding those pistons and cylinder walls together. The number 6 and number 8 cylinders were in the roughest shape, and it required about a week of soaking with the evaporust. But then one day we looked at it, and the fluid had all drained into the pan, so we knew it was ready to come apart. Before we pull these pistons out of their bores, there is a tiny, easily overlooked detail on the deck of this block that tells a massive story. Right next to each cylinder, stamped directly into the machined iron surface, is a single letter. You can't see it because of the rusty deck surfaces, but a quick time jump to the future will show what I mean. Now, look at the top of the piston sitting inside that exact cylinder. It is stamped with the exact same letter. In the Oldsmobile Lansing plant, these letters were the factory's version of precision blueprinting. When the engine blocks came off the final honing machines, they weren't all perfectly identical down to the microscopic level. So the line workers measured every single bore with a micrometer and assigned it a letter grade, usually A, B, C, or D, based on variances of just a few 10,000ths of an inch. Once the block was graded, the assembly worker would go to the parts bins and pull a piston that had been machined to that exact corresponding letter grade. An A bore got an A piston. A C bore got a C piston. This ensured that the piston-to-wall clearance was absolutely flawless across the entire engine, straight from the factory. Finding these letters matching perfectly is the holy grail for an engine forensic teardown. If this engine had ever been rebuilt by a local machine shop, the deck surface would have been machined flat, or decked, completely erasing those block stamps. And aftermarket replacement pistons don't carry these factory letter grades. This wasn't just an Oldsmobile trick. Select fitting was a standard practice across General Motors. Because mass production machining in 1972 couldn't guarantee every cylinder was identical down to the microscopic level, the factory graded the parts and matched them by hand on the assembly line. Finding these matched stamps today proves the incredible level of precision GM put into their heavy-duty engines before the era of modern computer machining.
Hang on there a second. That was not always the case on the W30 engines. We did it differently.
I stand corrected, Doc, as we can see here from this excerpt from the maintenance manual. Because your engineers wanted more piston-to-wall clearance on the serious high-performance W30 street engines, they specified that a D-bore should be matched with an A piston. They knew that these engines were going to be abused a quarter mile at a time, often under not ideal conditions, and overheating and the subsequent piston scuffing was a real possibility. Out on the water, however, with a constant supply of cold lake water, the extra wall clearance wasn't deemed a benefit or necessary. With the top end disassembled and the pistons removed, we then pulled the front cover to get to the camshaft. But before we could slide the cam out, we ran into a classic Oldsmobile calling card, the factory nylon-coated timing gear. Back in the 1970s, engineers coated the aluminum upper timing gears in nylon to keep the engine running whisper quiet for the luxury car crowd. It is incredible to see one in perfectly pristine, zero-hour condition like this. But make no mistake, after sitting dry for 50 years, this plastic is a ticking time bomb. If we had tried to fire this engine as is, that brittle nylon could have shattered, jumped the timing chain, and sent those massive valves crashing right into our high-compression pistons. With the timing set out of the way, we could finally extract the brain of this operation, the camshaft. This is the piece that dictates exactly how and when this engine breathes. The only casting numbers on this camshaft related to the raw core that was used to make it, so that couldn't help hide it. But then we saw the proof. Right there, perfectly preserved on the raw iron, are 3 distinct green paint stripes. Just like the dabs of paint we found on the valve springs, the assembly line workers used color codes to grab the right camshaft out of the bins without slowing down to read part numbers. When we cross-reference this with the 1972 factory assembly manual for our specific engine package, it lists part number 409691. And right next to that part number, the manual explicitly dictates the visual identification code, 3 green stripes. Part number 409691. Lift 0.474 inches. Intake /0.472 inches. Exhaust duration 286 degrees /287 degrees. In the Oldsmobile hierarchy, this is royalty.
Ah, behold, the glorious 691 cam. A marvel of engineering, wouldn't you say? Pure brilliance.
This exact profile features 0.474 inches of intake and exhaust lift, with a massive 286/287 degree duration. This is the legendary factory W30 camshaft. General Motors designed this specific cam profile to take full advantage of those 80 cubic centimeter GA cylinder heads and the 10.25:1 compression ratio we calculated earlier. Finding these 3 green stripes perfectly intact is the ultimate payoff. It proves we have the exact heartbeat of a 1970 muscle car, perfectly preserved in a heavy-duty marine wrapper. With the top end completely decoded, we flipped the block over and pulled the oil pan to inspect the foundation of this engine, the crankshaft. This is the backbone that has to handle every single ounce of that 500 foot-pounds of torque. In the earlier days of Oldsmobile muscle cars, specifically the 425 cubic inch engines and some early 400s, the factory used forged steel cranks. But by the time the massive 455 was introduced, Oldsmobile had transitioned to nodular iron. This crank has a large N cast right into it. That's the identifier for nodular iron. Some old-school purists turn their noses up at cast iron, but nodular iron is a completely different animal. Through a specific metallurgical process, the graphite inside the iron forms into microscopic spheres or nodules instead of flakes. This gives the crankshaft incredible flexibility and strength, preventing it from snapping under extreme loads. Let's get Doc Olds to explain it to us.
In regular cast iron, sharp graphite flakes create stress points. This causes brittle fracture under pressure. Nodular iron spherical graphite allows for ductile bending. The material deforms instead of breaking. Nodular cast iron spherical graphite nodules prevent crack propagation. The material bends and absorbs energy instead of shattering. Compare this to regular cast iron, which fractures instantly.
These factory nodular cranks are legendary in the Olds community, easily capable of handling massive horsepower without breaking a sweat. It is more than enough backbone for a 5,000 RPM marine application. But the most incredible part of this bottom end isn't just the metal, it's what is painted on it. Look at these vibrant red and green paint splashes on the counterweights. After sitting in a dark crankcase for 50 years, they look like they were painted on yesterday. Earlier, we talked about the select fit process for the pistons, where the factory graded each cylinder with a letter to ensure perfect clearances. These paint marks are the exact same blueprinting process, just applied to the bottom end. When this crankshaft was machined, the main and rod journals weren't perfectly identical down to the 10,000th of an inch. So the factory measured each journal and painted a color code on the adjacent counterweight. A green mark typically meant the journal was machined to absolute standard spec. A red mark meant it was running a fraction of a hair tight. When the assembly line workers saw a red or green splash on the crank, they didn't have to measure anything. They simply reached into the corresponding red or green bin and grabbed a bearing shell that was minutely thicker or thinner to match. This guaranteed that the oil clearance across every single bearing was utterly flawless. Seeing these colors perfectly preserved is the ultimate proof that this engine is an untouched, factory blueprinted masterpiece. Before we wrap up this teardown, there is one final, incredibly cool piece of engineering hidden right on the front of this block. If, like myself, you are used to rebuilding traditional Chevrolet or Pontiac V8s, you expect the ends of the main oil galleries to be sealed off with standard, solid plugs. They rely mostly on internal splash oiling to keep the front end of the engine alive. But Oldsmobile did things differently. Look closely at this threaded hex plug sealing the passenger side oil gallery. Oldsmobile engineers purposefully drilled a tiny, calibrated pinhole directly into the face of it. Because the oil in that gallery is under high pressure, this hole acts as a dedicated spray jet. From the second this engine fires, that jet forcefully sprays a constant stream of oil directly onto the timing chain and that fragile nylon camshaft gear we pulled off earlier. And they didn't stop at the front. At the back of the block, there is another specifically drilled plug doing the exact same thing, spraying a pressurized jet of oil directly onto the distributor gear, which has the heavy burden of driving the oil pump. It is a small detail, but it perfectly encapsulates what we have uncovered today. Between the massive GA cylinder heads, the high compression pistons, the legendary W30 camshaft, and this overbuilt pressurized oiling system, this isn't just a leftover boat anchor. It is a 0-hour blueprinted time capsule from the peak of the muscle car era. And now that we know exactly what is inside, it is time to build it back up, ditch that nylon gear, and finally hear this 390 horsepower monster scream. If you enjoyed our presentation, please do us the favor of pressing the like and subscribe buttons, and let us know if you'd like to see more on the resurrection of this legend. It won't ever see the water that it was born for, but there is a nice 1969 Cutlass convertible that just might be the home this mill needs.